Okay, welcome back, everyone. How is the homework going? I don't want to spend that much time on it because I've been spending a little too much time on homework in class lately, but I can answer a couple of questions. Let's see, here's time. And I know by time 4, I've had 2 arrivals. I don't know exactly where they were. I'm not saying the second arrival happened at time 4, but I know there's 2 of them in there. And 4 is 2. And so I want the time of the 5th arrival. If you start looking at the process at time 4, the time until the next arrival is still exponential by lack of memory. And I need 1, 2, 3. I need 3 more arrivals. So I need to wait through 3 exponential times. The subscripts aren't right, but it doesn't matter because they're IID. So it sounds like exactly what you're saying, but you wanted it somehow more formally. So the time here is going to be 4 units of time plus the expected value of 3 exponentials, which is a gamma, or you can run the expectation through, and that's not an equal sign, that's a plus. So 1 over lambda plus 1 over lambda plus 1 over lambda, or you treated them as one random variable as a gamma. I guess we could do this a little more formally. So as what I did was, just for other people, the time until the next arrival measured from here should be exponential, but I don't know when that time was. So it's kind of like I just came in and started looking at the process here, and by lack of memory, it's still exponential. So I drew 3 exponential inter-arrival times, and I guess I should have labeled them T3, T4, and T5, but they're all IID, so it doesn't matter. And so we're using lack of memory to ignore this part here. So I think you can probably do this more formally by conditioning on, I didn't mean for you to do all this, but if you know that there were 2 arrivals by time 4, like as far as I'm concerned, you're done. But if you know there were 2 arrivals by time 4, you can do some of the stuff we talked about last time to say that the time of the second arrival is the maximum of 2 uniform 0-4s. It's like an order statistics problem, because if you know there's been 2 arrivals by time 4, you can actually find this time and this time. They're going to be distributed as the min and max of 2 uniforms in there. And then you could actually condition off of this time if you did it that way. I don't think I want to drag the class through that, but we can talk more about that in an office hour. Okay, let's do some new stuff, which is the first thing I want to do is something I've been talking about for a week, maybe more than a week, and that is proving the exponential inter-arrival time properties of the Poisson distribution. And so in order to do this, I need to talk very briefly. You already know how to do this, but we've never done it. So conditioning, I think you know how to do it. Conditioning on continuous random variables. That's one word, continuous random variables. Okay, so just recall the discrete case in one line. If you want to find a probability involving some random variable x, you could rewrite it as the sum over y of the probability that x equals x given y equals y times the probability that y equals y. And the intermediate step to show that would be to first write this as the sum over y of the probability that x equals x, comma, and y equals y, and then break it up into a conditional times a marginal. And it's going to be the same thing in the continuous case. It's just that they're not probabilities. So this is going to become a conditional PDF, and this is going to be a marginal PDF, probability density function. So in the continuous case, we're going to have some joint PDF f of x comma y, x, y, and we're going to use the fact that the conditional PDF is defined as this, sorry, there should be a line there, is defined the same way it's defined. This is by definition, the discrete case. So this is defined to be the conditional PDF over the marginal, which is why we can write the which is why we can write the joint PDF as a conditional times a marginal. So this, let me back up here with a color. This is actually the definition because we can't interpret these things as probabilities. So it's sort of just like it's been defined in the discrete case, and then we analogously pull it into the continuous realm, and we're set on this definition. So I can write this as a conditional times a marginal. And now let's write a marginal PDF in terms of like, let's condition on another random variable. So if I have a marginal PDF for X that I care about, but it's not easy to compute, I could write this as the integral minus infinity to infinity of the joint PDF for some X and Y and integrate out the Y. And then I can use the fact that that joint PDF can be written as a conditional times a marginal. So now we have exactly what we started with in the discrete case. You know, this is the continuous random variable version of this, which we've been doing all along. So it shouldn't be too surprising. And of course you can go directly from here to here. I'm just trying to show you why we get there. And then just one more thing. If you want to compute, say, a probability that X is greater than X or some kind of probability involving X, and it's easier for you to bring Y into the problem, this is just going to be the integral from minus infinity to infinity, which may get restricted depending on the values Y can take on, of the probability that X is greater than X, given Y equals Y times the PDF for Y integrated over Y. We've talked about this conditional thing before. For continuous random variables, the probability that Y equals Y is 0, which is why I'm not writing, this is not the probability that Y equals Y. But once it's observed and fixed, you do have a value. So it is okay to have an equals in a conditional random variable statement if it's after a conditional or given line. And so this is kind of what we were doing before as well, but if you want to prove this, then I would just say the probability that X is greater than X, and I just made this one up. I mean, we might want other probabilities involving X, but I wrote this as the integral, or I would write this as the integral from X to infinity of the PDF for X. And then I would condition on Y, which is what we did before. So I would rewrite that PDF for X as an integral minus infinity to infinity fx given y, x given y, and then the marginal for y, dy, dx. So this is just using what we just did above to write out that marginal for x. And then if you interchange the order of integration here, so if I'm integrating with respect to x first, I've got the conditional for x given y, and then the f of y, I don't need to integrate with respect to x. So let me pull that kind of out here. So the point was I changed the order, and this is how you compute the probability, right? If you integrate, say, x to infinity, the PDF for x, you are computing the probability that x is greater than x. That's what you're doing. And so what we're doing here is computing the probability that x is greater than x, but in conditional land. So that's what we wanted to show. It's up here, this top line is what we were trying to show. So it basically works like it does in the discrete case, even though these aren't probabilities. And I know that was kind of rushed, but I'll slow down when we do some examples involving that today. Okay, so we have a rate lambda Poisson process, and we want to show this thing I keep claiming, and that is that the interarrival times are IID exponential with rate lambda. By the way, one more thing I should say is how to show something is independent. There are many ways to show independence. When I'm talking about events, well, when other people talk about events, they define independence to be the probability that the intersection factors into the product of the probabilities. And I prefer, I mean, you can use whatever you want, but I prefer to say that they're independent if the probability that A given B happens is just the probability that A happens. So this is equivalent to the above expression as long as the probability of B is not zero, because this is the probability of A intersect B over the probability of B. So if you move this probability of B to the right-hand side, you've got the original independence equation. But I really like this version of it because it says, what is the probability that A occurs given B occurs? It's just the probability that A occurs because they don't depend on each other. The same thing for random variables. We can say that X and Y are independent. Of course, we can say if the joint PDF factors into the product of the two marginals, but we can also say if the conditional PDF for X given Y is just the PDF for X. Same reasoning, take the left-hand side of this equation and write it as the joint PDF divided by the marginal for Y, and then move the marginal for Y over, and you're just seeing factoring of the joint PDF for X and Y. And yeah, you have to be a little careful that you didn't divide by a zero. You have to kind of consider that case. But this is kind of like, this is how I like to show independence, and I think it's particularly useful in what we're about to do. Sorry, I'm just going kind of fast. Okay, so I'm gonna let, what the heck? I'm gonna let T1, T2, etc. be the inter-arrival or inter-event times of a rate lambda Poisson process. I don't know, sometimes I hyphenate that, sometimes I don't. I always hyphenate inter-event, but never inter-arrival. The inter-arrival times of a Poisson process with rate lambda. So my claim here is that the T's are IID, independent and identically distributed exponential random variables with rate lambda. Okay, and so let's show it. We already showed the first one is exponential, but it didn't take very long, so I'll do it again. If we look at T1, why is that there? Let me write, consider T1. We looked at the tail probability, the probability that T1 is greater than some T. And so here's a number line and here's a T, and the time of the first inter-arrival time is the same thing as the first arrival time. And so if it's greater than T, that happens if and only if there were no arrivals up to time T. So this is the same thing as the probability that the number of arrivals by time T is 0. And this N of T is a Poisson random variable with rate lambda times T, the length of the interval we're looking at. So this is e to the minus lambda T to the 0 over 0 factorial, and that's e to the minus lambda T. And if you recognize that as the tail probability for an exponential, you're done. If not, you can flip this around and do a little 1 minus on both sides. And if you recognize that as the CDF of an exponential with rate lambda, you're done. But if not, you can take the derivative of both sides with respect to t. Now, this thing is the CDF, the cumulative distribution function. So if I take the derivative, I get the PDF for T1. And on the right side, I get 0 minus lambda e to the minus lambda t. So I get positive lambda e to the minus lambda t. And now you definitely recognize the exponential PDF. let's go for T2, and then I'm just going to say dot, dot, dot. I want to show two things. One is that T2 is exponential, and the other is that it's independent of T1. So now I'm going to consider T2, which is not the second arrival time. It is the second inter-arrival time. So we have an arrival and another arrival. So this is T1 and this is T2. So T1 being the first inter-arrival time actually turned out to be the same thing as the first arrival time. But T2 is definitely not the time of the second arrival. The time of the second arrival is T1 plus T2. But I'm still going to take the same approach by looking at the tail probability, the probability that T2 is greater than T. And I would kind of like to think about this like a T1 again, which means I kind of want to make this horizontal, that's not horizontal, this vertical line here, kind of like time zero. So I'm going to condition on where the first arrival was. I'm going to write it rather generically. You don't have to write this line. I'm going to say T1 happened at time S, and then multiply by the PDF for T1 at S ds. So I said it was generic, and that's because T1 is an exponential and doesn't take on negative values. So this is going to be the integral from 0 to infinity of the probability T2 is greater than T given T1 is S times lambda e to the minus lambda S ds, because we already know that T1 is exponential. So we're trying to show something that's a property of the Poisson process. We need to get the Poisson stuff in there. And so now I'm going to rewrite this conditional probability in terms of the n of t process. So we have that the first arrival happened exactly at time s. And so now I want the probability that the next arrival is greater than t units of time away. So this is the, oops, this is the integral 0 to infinity of the probability of no arrivals. I'm sorry, I'm going to move that picture. Actually, I'm going to remove it. No arrivals in the interval s to s plus t, given t1 is s, lambda e to the minus lambda s ds. So it's, again, it's kind of like this became time zero. And remember how in the T1 case, I said the probability T1 is greater than T is the probability that n of T is zero, zero arrivals in that interval from 0 to T. So this is 0 to infinity probability n s plus T minus n of s is 0. And if we want to, you don't have to keep doing this, but I'm doing this at the beginning, the first few times we're doing this stuff. I want to translate the stuff on the right side as well. So this is saying that n at time s is 1 and n at time u is 0 for all u between 0 and strictly less than s. You know, if the first arrival happened at time s, then that's exactly when this process clicked up to 1, and it was 0 before that. And now I have the PDF sitting here. And now I can use the Markov property to drop this stuff. But I can also then use the independent increments property to drop this stuff. Independent increments. So we are down to the integral 0 to infinity of the probability n s plus t minus n of s is 0, lambda e to the minus lambda s ds. And this guy is a Poisson random variable, and the parameter is lambda times the length of the interval, which in this case is length t. Yeah, is length t. So this is the integral 0 to infinity of e to the minus lambda t. I wasn't going to write it, which is why I didn't make this have the right sort of height for a fraction, but just in case, I'll put all of that in there. And then lambda e to the minus lambda s ds. Right. So 0 to infinity. I can pull that e to the minus t out, so let's do that. Lambda e to the minus lambda s ds. And now I'm integrating the exponential PDF. This is a PDF. This is the region for that PDF. So this entire integral is 1. And we get e to the minus lambda t. Let me just scroll right back, sorry. We started with the probability that t2 was greater than t, and we got that this was e to the minus lambda t. And you know what else happened? Along the way, we showed that the probability that t2 is greater than t given t1 is s. So we translated that into the process, the n of t stuff, and then we got that this was e to the minus lambda t. That is something that we had in those steps above. I don't know if it's worth me scrolling through here. Yeah, maybe. So we had this, and we rewrote it like this, and we rewrote it like this, and we dropped stuff to rewrite it like this, and we got e to the minus lambda t because this stuff wasn't there. So what I'm trying to say is this is the same thing as the probability that t2 is greater than t, because that's what we got up here. And so this is enough to say that t1 and t2 are independent. But if you don't like it, this is also enough to say that the probability that t2 is less than or equal to t, given t1 is s, this is 1 minus this guy, which is equivalent to 1 minus this guy. Because I already know that those are equal from the line above. So I'm doing a 1 minus on both sides. And so this is equal to the probability that t2 is less than or equal to t. And if you take the derivative on both sides with respect to t, then what you have on the left side is the conditional PDF of t2 given that t1 is s. And on the right side, you have the PDF for t2. I know I'm kind of sloppy, extra sloppy today, and I'm just scrawling a lot of stuff. But what I'm trying to say right here is that if you know that this is equal to this, then you can do a 1 minus on both sides, and you get that this is equal to this. And you can take the derivative with respect to t on both sides, and you get the conditional PDF for t2 given t1 is equal to the PDF for t2, and which is one out of several ways to say that t1 and t2 are independent. Oh, did I make my conclusion about, yeah, hold on. Finish writing this. Independent. Back up here, this check mark thing is telling me that t2 is exponential with rate lambda. So we showed, number 1, that t2 is exponential with rate lambda, and number 2, that it's independent of t1. And etc. So if that's exponential, you can do it for t3 and condition on where you were at when the second event happened. So condition on t2, yada, yada. Okay, but here I think is the exciting thing. We just showed that for a Poisson process, the interarrival times, we almost showed, we have to do an induction here to really show it for everything. But we just showed that the Poisson process has exponential interarrivals. And in fact, if we have exponential interarrivals and the other two properties from the Poisson process, property I and double I, and we never mentioned the Poisson random variable, that's actually enough to say we have a Poisson process. So I claim that the exponential interarrivals coming from the Poisson process are an if and only if. And what I mean by that is definition 2 of a Poisson process. So a counting process, N of t, is a Poisson process with rate lambda. So I'm going to define it a little differently now. Is a Poisson process with rate lambda if, that's the lambda, looks like an x. The first I, there's going to be three i's again. I, double I, triple I. So we're going to start it just by convention. So you have 0 arrivals by time 0. Double I is going to be identical to what it was before. And for brevity, I'm just going to write it out in English. And that was the independent increments property. I can write this out longer by saying let S1 be less than S2, be less than blah, 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 less than Sn. And then I can look at the actual differences and say they're independent random variables. And the third thing used to be that the number of arrivals between time S and S plus t is a Poisson random variable with parameter lambda times t. But now it is that we have IID exponential interarrival times with no mention of the Poisson distribution. Now, to prove that this is equivalent, we do have to do one more thing. We have to go the other way. So clearly, I and double I are equivalent. They're exactly the same. And we just showed that definition 1, which is where we had the Poisson assumption here, gives us this exponential result. So definition 1 implies definition 2. I need to go backwards and to show that this triple I implies, along with the, it's all a package, that this will get me back the Poisson, the triple I from definition 1. So we have shown that, really we have, it's just been over several days. Might be hard to find all those pieces. So now, what should I call this? Should I have a claim? I'll call this a claim. Lame. I meant to get some graphic. I can't draw. Can you tell what this is? No. What? This is awful. I noticed in the transcript of the chat that every time I say Poisson process, it comes out as croissant process. It's me trying to draw croissants. Can't do it. I meant to actually get graphics before today's lecture. Okay, so my claim is that definition, what do I want to do specifically? Well, a couple of things. So definition 2 implies definition 1, i.e., so this is still part of my claim statement, the exponential interarrivals, not by themselves, also with I and double I, but will give us back the Poisson property, the triple I from definition 1. Poisson in triple I of definition 1. So let us prove it. So suppose I have a counting process that I is 0 at time 0, double I has independent increments, and triple I has IID exponential interarrival times. Then I claim it's a Poisson process. So I and double I for the original definition of the Poisson process are already satisfied. They're identical. But we need to go from the exponentials to the Poisson. So I want to show that n of s plus t minus n of s is a Poisson random variable with parameter lambda times t. Then we'll have shown that we have definition 1 holding, i.e., for any k in 0, 1, 2, on up, we want to show that the probability that n of s plus t minus n of s equals k, we want this to be e to the minus lambda t to the k over k factorial, and we want to get that from our exponentials. So let's do it. That's just what we want to show. Here is us actually showing it. The probability, so the left-hand side, the probability that n of s plus t minus n of s equals k, this is the probability of exactly k arrivals between time s and s plus t. So this is the probability of exactly k arrivals in the interval from s to s plus t. That's what that means. Okay, so I've got some time s. So I want the probability of exactly k x's in here. And I'm working off the assumption that the times between arrivals are IID exponential. So I'm going to use two things here. One is the lack of memory property to say that the time of the first arrival in that interval, this distance here is still exponential. It doesn't matter that the last one really happened way back. And I'm also going to use the IID-ness of the exponentials to write the next line, and I'll tell you where I'm using that in case you don't see it. This is the probability that the sum as I goes from 1 to k of ti is less than or equal to p, and the sum as I goes from 1 to k plus 1 of ti is greater than t. So I am using IID-ness here. So this was both, okay, so number one, I used lack of memory just to get that this very first time is exponential. And then I used IID-ness to not worry about the subscripts, because really this time, this first inter-arrival time, that when we start looking at time s, is probably something like capital T 15. I don't know exactly where we are at this point, but it's another exponential, and the next inter-arrival time is another exponential, and the next one as well. So you might have noticed that I'm actually using T1 and T2 when really those happened way back here. So again, number one, I use lack of memory to not worry about when we start looking at the process at time s that we interrupted something. And I also used it for an easier notation, so I didn't have to do some kind of like I equals 15 or whatever it is. I don't know what it is. So I used the IID-ness of the t's. It's adding up k inter-arrival times starting at time s and making sure that it's below time, below a total length of t. And also making sure that I can't fit one more in there. If I add one more, then it's suddenly up above the total length of t. Right. Okay, so I've got some gamma random variables here because we showed recently that the sum of exponentials has a gamma distribution. I'm going to rewrite this as the probability that W, which is one of my favorite letters for a gamma distribution, is less than or equal to t, and W plus t, which I'll define, is greater than t. And I'm going to say where W has a gamma distribution. So remember, when you add exponentials, the first parameter of the gamma is the number of things you added together. So in this case, k, and the second parameter matches that of the exponential. And t is exponential with rate lambda. I mean, it's probably a t 23 or something, but I'm just writing a t without a subscript to be kind of a generic exponential. And also, we have that W and T are independent by the assumption that all the T's were IID. So I have a gamma sum here. This is also a gamma sum, but it's the original gamma sum plus another exponential. So to find this probability, I'm going to condition on one of these two random variables. And I'm going to condition on W as opposed to T. And I'll tell you why after I write a few more lines. You'll be able to see why I chose this one. So I'm going to write this as the integral from minus infinity to infinity, or if you want to go straight to 0 to infinity, you can, because the W only takes on values from 0 to infinity. The probability that W is less than or equal to T, W plus T is greater than T, given W is S, times the PDF for W at S ds. I know you probably want to condition on the T because it has a simpler PDF, but if you condition on the T, after we simplify this, the thing that you're left with is going to be hard to write down. So let's start simplifying this. This is 0 to infinity because this PDF is 0 when you plug in negative values of S. The probability that W is less than or equal to T, W plus T greater than little t. And then I'm going to write that. I was just going to write the PDF in, but maybe I should already start filling this stuff in. Maybe I should. Because W is equal to S, so I haven't finished this line, then this is little s. So I'm going to go ahead and plug that in. And I'm going to plug in little s for the other W over here. And then I'm going to finish off the line with the appropriate gamma. So this is the same line. The appropriate gamma PDF. 1 over the gamma function at k, lambda to the k. We're writing it as a function of s, so s to the k minus 1, e to the minus lambda s ds. So over here in this probability, I've got two constants. This is, yeah, I've got something else to worry about as well, but it's kind of like the probability that 1 is less than or equal to 3, or the probability that 3 is less than or equal to 1. It's either 1 or 0. So I get to drop this as long as I limit my s's to being less than t. So this entire probability is going to be 0 if the s ever gets up above t. And for that reason, maybe I should write that. This is 0 if s is above t. So for that reason, I get to rewrite this as the integral as s goes from 0 to t of the probability. And then I've taken this guy into account. So I'm just going to write the other stuff. Okay. Now, over here, I only have a t on the left side and only a w on the right side. And because they're independent, to compute this probability involving t, I don't need to know anything about the w. And that means that I can drop this w since w is independent of t. So one mistake I see a lot is, so from here to here, I plugged in the information known about w. And so now there's no w's on the left side. But that doesn't mean I get to drop the fact that w is s, because the random variable t in general could actually be dependent on what w is. But I do get to drop the w when I'm computing a probability for t, because w is independent of t. Okay, let's bring it on home. This is the integral from 0 to t. This is, I don't want to write this whole line in here. So let me say that, let me rewrite this as the probability that t is greater than t minus s. And that's actually okay. It's not going to be 0 anywhere because we're in the regime where s is less than t. So this is always greater than 0 in this integral. And t is exponential with rate lambda. So this is one of those tail probabilities. This is e to the minus lambda t minus s, using the fact that t has the exponential distribution with rate lambda. And then everything else. Here's why I wanted to condition on w and not t. Because if I came down to a probability involving W being less than or greater than something, I don't know the CDF for the gamma distribution. You can't write that in closed form except in a few cases. And so if I had conditioned on T, then I would have been stuck at this point. But I do know how to write this down if T is exponential. Okay, let's combine things and pull things out that we don't need. I have an e to the minus lambda s, and then over here, that part would be an e to the positive lambda s. So that's going to cancel. And I'm integrating with respect to s. So let me pull out the e to the minus lambda t, the 1 over gamma of k, the lambda to the k, and I'm left with 0 to t s to the k minus 1 ds. Now this guy is s to the k over k evaluated from 0 to t, which just gives us t to the k over k. So putting it back together, the entire thing is e to the minus lambda t, lambda to the k, 1 over gamma of k, t to the k over k. But remember, k is an integer, and the gamma function of k, an integer, is k minus 1 factorial. And then I'm going to combine that with this k to say that I have k factorial in the denominator. And I'm also going to combine the lambda to the k and the t to the k, and we're done. We have e to the minus lambda t to the k over k factorial. And that's what we wanted. We wanted to get that Poisson probability in there, starting with the exponential interarrival time assumption. That was pretty much the coolest thing you've seen since 150 today. This completes the proof that definition 2 actually implies definition 1. Starting with the exponentials, we can get the Poissons. I have a third definition, but I don't think we're... So what I was going to do here was a simulation break. I don't have time for that either. So let me just do a little teaser for the third definition, because this is going to... Oh, more I talk and groan about the time that's going by. So in our third definition, we're going to use little o functions, little o. And so I'm going to be writing a little o of h. And this symbol represents a function f of h or g of h or whatever you want to call it, such that the limit as h goes down to 0 of f of h over h is 0. So what is this saying? This limit result is saying that the f of h definitely has to be going to 0 because the denominator going to 0 is making this blow up. So it's saying that my function f of h is going to 0 so fast that it can kind of kill that denominator and still make the whole thing go to 0. So we're going to use these little o of h's every time we want to write things that are going to 0 kind of fast. And the little o's are going to be the basis for definition 3. Next time on Markov chains.
So Dex is out again, and I'm pretty sure I know where he is. Dex. Dex. Oh. Dexy. Come on, Dex. Oh, Dex. Really? I see studs in the wall. Dex, come on. Oh. Where are you, Dex? I think I'm gonna find you if I follow this. Dex. Seriously?